Hello and welcome. In this video, we're going to take a look at systems of linear equations. But we're going to take those linear equations and we're going to reduce them down into what we call an augmented matrix. And then once we get into a matrix form, we can look at some row operations, things that we can do to manipulate that matrix, and ultimately kind of get an idea of what our goal is in order to find a solution to the system of linear equations. So let's look at an example of a system of equations consisting of three linear equations in three variables. And I've chosen x, y, and z here, but it's also just as well to use x1, x2, and x3. Now, whenever we write down a system of linear equations, we're going to be trying to eliminate variables and try to reduce the number of variables until we can get a solution. And ultimately what we're really doing there is trying to look at the coefficients in front of each of the variables and trying to get most of them to be a coefficient of 0. And since we're really mostly just dealing with the coefficients, when we're adding terms together, really all we care about is what number goes in front of each variable. We can reduce this. We can take a look at just the coefficients here. So let me highlight all of the coefficients, including there seems to be one term that's missing here. Okay, now I've also included a 1 in front of the x, because if we just have a single x, it's taken to be the coefficient as 1. Now what we're going to do with all of those is really highlight those, make them the most important things, and start writing out a matrix, an array of values. In this case, an array of just the coefficients. And so since there are three variables and three equations, we have a 3 by 3 matrix, and this is called the coefficient matrix. Now the other numerical values in here are also important. They're on the right hand side. These values on the right hand side are simply the constants. They have no variables. Those are also equally important so that we can get the solution for x, y, and z. So what we're going to do is we're going to make sure that we have some way to tell the difference between coefficients and these constants by putting a vertical bar, and we'll have our constants on the other side of this divider. Now, altogether, this is one single problem, and rather than just having an array of values all around the screen, we put square brackets around the entire thing, and we call this an augmented matrix. A matrix is simply just an array of numbers represented in rows and columns. And it's an augmented matrix because at the right-hand side here, we've included a column of just the constants. Okay, if we didn't have that extra row, or sorry, the extra column of constants there, then we would just simply call this a matrix. But in this case, we have an augmented matrix. Now, it's important just to remember that each of these columns does represent a variable. We have a column for x, a column for y, a column for z, and then for our augmented matrix, we have a column of constants. And this becomes a much more compact form of representing the entire linear system of equations. We can then start to do certain operations here with multiple equations, and now really just refer to each equation as just a row of the augmented matrix. Now, try to think about what a solution to a system of linear equations would look like. We want to have a value for x, y, and z in this example. So what would that look like if we were to write that as a matrix? Well, if we were to write, let's say, as an example, a solution to any sort of three variable problem might be something of the form, x equals 2, y equals 5, z equals 1. This is another example. This may not be the actual solution to the previous example. In fact, I'm fairly certain it's not. I'm just making these numbers up. But let's suppose that this is a solution. Well, even this can be written as an augmented matrix. Start spacing things out so x has its own column, y has its own column, and z has its own column. And even though it looks a little bit ridiculous, that's exactly the same thing. And now, in terms of an augmented matrix, we just have to put zeros wherever we have none of a variable in an equation. So 1x, put 0 y's and 0 z's, added together equals 2. We have no x's, we have 1 y and no z's, added together equals 5. We have no x's, no y's, and a single z add together to equal 1. And so even the solution can be written as an augmented matrix. And this is what we would like our final augmented matrix to look like if we can just do some operations on it. And this is an example of a reduced row echelon form. What is that? Okay, well, there's sort of 4 criteria for having a matrix or an augmented matrix in reduced row echelon form. So the first one is any rows that are consisting entirely of zeros, they would have to be at the bottom. They are below any rows that have any non-zero entries. So that should be pretty straightforward. Just move those rows below. And we're going to talk about row operations, but the idea of moving a row from one place to another is no different than just writing the equations in a different order. So that's a pretty easy one. The next one, the first non-zero entry in any row is a 1. Okay, well, in any row that's not entirely all zeros, just make sure the first non-zero that you get to is a 1. And let's call this thing a leading 1. It's the first value in a non-zero row. So it's going to be the leading entry, and make sure it's a 1. Now in consecutive non-zero rows, and we'll very likely we'll have more than one row that's not all zeros, the lower leading one should be further to the right of the upper leading one. So if you're hitting another row and it has another leading one, make sure that you're going down and to the right. And you can kind of see that in this last example. Now, the last one, any column of the coefficient matrix that has a leading 1, better make sure that all of the other entries in that column are all zeros. So here that in that last example, you can see the leading 1 sort of form a staircase. The leading 1, and then we move to the right, and then we get the next leading 1, we move to the right, and we get the next leading 1. And anytime that you see a 1, then the rest of the entries in that row are zeros. We don't have any rows that are entirely zeros, so we don't have to worry about that first criteria. And so it meets all 4 criteria, and we would say that this example is in reduced row echelon form. But we can also look at many other examples that may not be quite that simple, that would still technically be in reduced row echelon form. And I'll just give you a couple examples of some maybe strange looking cases, but they're still in reduced row echelon form. Okay, here are 3 other examples of matrices in reduced row echelon form, and I have highlighted the leading ones. And you can see that if there's ever a row of all zeros, that needs to be at the bottom. That would be this example here, the first one. The first non-entry in any non-zero row, of course, is a 1. So you can see I've got those highlighted in the non-zero rows. If you look at all of the green rows here, the leading entry is a 1. Every consecutive non-zero row, you can always see that we've got sort of a staircase here of going over and down to get to the next leading 1. And we can also see that in any of these columns that have a leading 1, that the other coefficients are all zeros. So these are all in reduced row echelon form, or if you wish, we can call this RREF for short form. Now, that's our goal, because if you think about it, solutions have that sort of form, where it's just x equals, y equals, z equals. Those are all sort of the leading ones, and that means that we've solved for a variable. Well, let's see. Think about things we can do with equations. We can exchange equations. That's not a problem. Well, that becomes what we call one of our row operations right now. Another thing that we do when we are doing elimination is we can scale any row. We can multiply it by any non-zero value. Again, now that's going to be becoming a new operation for a row of a matrix. And then for elimination, we tend to add rows together. And then that is a way that we can eliminate a variable, in which case now in our matrix notation, that's how we get an additional 0 in there. So let's talk about row operations. The first row operation is the most basic. We can interchange any 2 rows. And a good way to make sure that you're keeping track of several steps if you have to do lots of operations on a matrix is to introduce a little notation for yourself and for the person marking your assignments, just to indicate what it is you've done. And so let's suppose that you wanted to interchange two rows. We could have row I interchanging with row J. So row 2 interchanges with row 3, for instance. And all that would be doing is just swapping rows and rewriting the same matrix. Now, the next one is also basic as far as common operations go with algebra. And that's, you can multiply both sides of a linear equation, or any equation for that matter, by some non-zero value. Now, when we take an equation and we multiply it by some non-zero value, we are going to replace that equation with a new one. And so in this case, we are replacing a row with a non-zero multiple of itself. And because it's a replacement, what we're really doing is we would be taking some row, we could call it row I, and we're replacing it with some multiple, let's say A times row I. As long as A is not equal to 0. Because if you take an equation, you multiply both sides by 0 and you replace it, then you've just got 0 equals 0, which is true, but you've lost information from the problem, and that will change your solutions. So our third one is a little bit more complicated. It involves a little bit of multiplication and addition or subtracting. And that's where we can combine two equations together and form a new equation, hopefully with the goal of eliminating a variable. And that is our third row operation. So in this case, we're going to take a row, we're going to take another row, add them together, and replace. And while we're at it, we can add a multiple of another row. So in this case, let's imagine we took row I, and that is now going to get replaced with row I plus some multiple A times another row, let's call it row J. So now we could take row 3, and we could add a multiple of 2 row 2s to that. And just like we would add term by term when we have the equations, we are going to be adding column-wise as we add values in the coefficient and constant augmented matrix row columns. Okay, well, let's just take a look at an augmented matrix and see how we would use this notation and use these operations to transform into an equivalent augmented matrix. Okay, so here I've just got an augmented matrix. You can see it's a 3-variable problem, and we've got 3 equations. So let's just see what interchanging rows would look like. So whenever we want to do one of these operations, we get an equivalent matrix. And rather than using the equal sign, it might make more sense to use an equivalent sign. So this symbol, not just an equal sign, but with the arrows on both sides, this would mean equivalence, or is equivalent to. So first operation we might want to do, we could say that this is equivalent to, and write a new matrix right below it. And in this operation, let's suppose that the first thing we want to do is we want to exchange row 2 and row 3. So we would write row 2 exchanges places with row 3. Row 1 is unaffected and it remains exactly the same, and all we're doing is exchanging the bottom 2 rows. And there we go. It's not necessarily a useful operation, but when we combine multiple operations together, we might be able to get closer to our goal of a reduced row echelon form. Now let's try the second row operation. Replace any row with a non-zero multiple of itself. Well, maybe one example of where that could be useful is looking at this first row, everything seems to be a multiple of 2. Well, why don't we take row 1 and let's replace it with 1/2 of row 1, or 0.5 times everything in row 1. So in this case, row 2 and 3 are unaffected, and we can just rewrite them. Multiplying every entry in the first row by 1/2 will give us 1, 3, -4, and 2. So now I've combined two row operations together. But so long as I just follow row operations, even this third augmented matrix is still equivalent to the original. Now, there might be one other thing that we could try doing here, and this is actually going to be maybe helpful for us to try getting some extra zeros in this augmented matrix. I can see that in row 2 I've got a -1, and I see that in row 1 I've got a +1. I could definitely take row 2 and replace it with row 2 plus a row 1. Now what's really important here is knowing that row 1 isn't going to change. Row 1 is what we're using to add on to the values in row 2. So take a moment, take the value of row 2 in the previous value. In the previous matrix, row 1 plus row 2, 1 plus -1 will give us 0. In the second column, row 1 plus row 2 is going to give us 5. In the third column, 2 plus -4 is going to get us -2. And in the final column, 12 plus 2 is going to get us 14. Now, when you're feeling a little bit brave, then maybe you can do more than one row operation at once. But it'd probably be best to use row 1 again, since we're not affecting row 1 during this process. It might be worthwhile to see what we can do with row 3 from the previous augmented matrix while we're at it. Seeing as how we've got a 3, let's see if we can make that a 0 somehow by using row 1. But row 1 has an entry of a 1 there, so we would have to subtract 3 times row 1. That's still a multiple. Row 3 would just become row 3 plus a multiple of -3 times row 1. Okay, now the algebra starts to get a little bit more powerful. We need to take 3 and we need to subtract 3 times 1. That's going to get us a 0. Our next entry, take a 1 and subtract 3 times 3. That becomes 1 minus 9. That becomes -8. Next column over, we have a 0. It's not going to remain a 0 for long though, because we are subtracting -3 times -4. That means we're adding 12. Well, we don't have a 0 there anymore, but that's okay. And last but not least, in the last column, we have 5, and we could subtract 3 times 2. That would be 5 minus 6, and that's -1. When in doubt, it may be helpful to write most of these little operations on the right-hand side. Just make them legible on the right-hand column so you know what you're doing on each individual column. But eventually, you can start to do some of these basic addition, multiplication operations in your head or with a calculator. Well, it looks like we're on our way to getting into a reduced row echelon form. We've certainly just tried a few row operations, and it looks like we're starting to get a leading one where we want it to be. But there should be a way of performing these operations in a much more routinely manner. But I'm going to say that for a future video. We're going to look at the Gauss-Jordan elimination method. And what we're going to be doing with that method is performing row operations in a more algorithmic sort of manner, something that is just a routine. And it's going to be the most efficient way in many cases, and even if it's not the most efficient in some cases, it will be at least a very rigorous method that you can follow with predictable results. And that'll be for our next video. So thanks for watching. See you later.